Okay, so today's our last lesson, and then we're done our third unit. And yeah, then we're just really finishing tasks till Christmas. So, quick reminder of what we're up to for the next week and a half. Today's our last topic. Tomorrow is Wednesday. Tomorrow's only Wednesday, guys.
What?
Tomorrow's only Wednesday.
It's like it's Wednesday today.
I know, or Thursday. Okay, Wednesday, Thursday, Friday, you guys are going to do 2 different labs. And I don't care what order you do them in. So I'll probably need about 45 minutes tomorrow just to kind of demo how to do the 2 labs. And then over the rest of the week, I want you guys to finish the 2 labs whenever. Okay, so you can do the titration one first if you want. That one will probably take a little bit more time because titrations, like I demonstrated the other day, you kind of have to do like a drop-by-drop method. And so it's a little bit tedious. Okay. The other lab we're going to do is going to be way quicker. What we're going to do is we're going to add some magnesium to hydrochloric acid. Okay. Do you guys know what magnesium and hydrochloric acid do when they react with each other?
Magnesium.
Maybe we should just write out the equation. Maybe it'll be easier to visualize. If we take magnesium ribbon, so this will be Mg solid, and we add to HCl, what kind of reaction will take place? Single replacement, yeah. So it's going to make magnesium chloride. Now, it's not the magnesium chloride that I'm interested in so much. It's the other byproduct. Good, hydrogen gas, yeah. We're going to do a gas collection lab. Now, you guys have already done a little bit of work with gases before. How do you collect a gas? What did you say?
I don't know what the camera.
Maybe you're saying, someone's saying it, I hear it. Good job. Displacement of, good job, well done. Can I say that louder for everybody here? Good job, by the way. Displacement of water is what we're going to do. Okay. We're going to do the exact same thing we did in the butane lighter lab. We're going to turn a graduated cylinder over upside down. We're going to run some tubing from our reaction container underneath and into the graduated cylinder. And as the reaction bubbles, all of the bubbles normally would just escape into the atmosphere and we wouldn't care. But this time around, we're going to put a lid on top of it, force all the bubbles to go through a tube and displace water. It means that we're going to get a volume. Does that make sense so far? Well, that volume is the actual volume. We're going to also calculate theoretically, based on stoichiometry, how much we should have gotten, and we're going to calculate a percent yield. And again, like with the lab we did a little while ago, hopefully we get a percent yield of close to 100. Now, when you guys did your last lab, I think the best percent in the class was like 50, is that about right? And most were like in the 30s. So I'm hoping for this next lab, there are much less reasons for us to have errors in this next one, so I'm hoping for close to like 80 to 90% success on this next lab. It's very simple. Like all you literally have to do is set up a few things, put a piece of magnesium into hydrochloric acid, put the lid on and let it bubble, and bubbles will just take the place of water. So those are our last 2 labs, a titration and a gas collection lab. Next week then, I said this the other day, I don't care when, but at some point during next week, I need you to write 1 more quiz and 1 more unit test. And you guys can stagger those as you see fit. So I have them scheduled on Tuesday, Thursday, but honestly, I don't really care. Just the only thing for you guys to note is we are going to do a math quiz later this week and a math quiz next week as well. So if you want to kind of choose how you want to stagger those tests. Do you guys have any social tests or anything coming up as well?
We just had one yesterday.
So you guys are probably good in social for a while.
Yeah.
Okay, so basically in each of my 2 classes, that if you have both of them obviously, basically you have 2 tests to write in the next little while, 1 in each class. So. Any questions? Okay, let me do a quick summary of our unit then, before I do our last set of notes. My whole goal behind this unit is to talk about some of the practical side of doing chemistry. And I hope this has been, I don't know, maybe enlightening is the word, where you get a chance to kind of think about what a scientist, what a chemist actually is trying to accomplish. I love the analogy of baking or cooking. Your goal is to make something, right? I mean, that's ultimately what a chemist is trying to do, is trying to use a chemical reaction to make something that's useful. I mean, whatever that something happens to be. Maybe he wants to refine and make pure gold. Maybe he's trying to create a new oxide that can be put on the outside of a spaceship so it doesn't burn. I don't know. Does that make sense? But your goal is to basically produce, to react, to synthesize something. Okay. There are a lot of practical questions you have to ask them. One of the first questions you have to ask is, how do I do it safely? So, like, what are the products going to be? What are they going to look like? Are they going to explode? Are they toxic? Other questions you have to ask are, what is really necessary? We talked about spectator ions, the concept that if I want to make silver, for example, say that's my goal, I could make silver a bunch of different ways. I could say take silver nitrate and add it to magnesium, and it would give me magnesium nitrate and solid silver by itself. That's my goal. Is this the only way, though, to make silver? Who are the spectator ions probably in this? Well, who is the spectator ion in this example? Yeah, nitrate. Yeah. Because really, if I changed out nitrate for, say, chloride, does that actually change the example really all that much? No. So maybe in my lab I don't have silver nitrate, but I have silver chloride. That's like my analogy of butter versus margarine. You know, is there a reasonable substitute you could use to solve your problem? Other things we need to talk about are the expected yield versus the actual yield. Pretty much every time you do a chemical reaction, you're not going to get 100% capacity. That's just a reality of life. I've given this analogy to a lot of you. Melissa wants to make a dozen cookies, but Kinsey and I are going to steal one each. Like, that's just a guarantee, right? So that means she's only going to have 10. It means she needs to really aim to make 14, so that when we steal a cookie each, then she ends up with 12. A percent yield is always going to be lower than what you're hoping for. So sometimes you actually have to aim to produce more. Does that make sense? Other things we talked about, once we learned how to do a bunch of math, we had a class right in the middle where we talked about colorimetry and some of the separation techniques. Sometimes you may end up making a product and you don't know what it is. Or you may end up making multiple products and you have to filter or separate them. So some of the techniques we need are things like filtration, crystallization, distillation, gas collection. You need to have some like methods to extract the product you're actually looking for. Does that make sense? And you might even need to try to recognize what it is based on a flame test or just a color test. Okay. One of the other things I wanted to talk about, this is kind of more today and yesterday's topic. One of the two keywords we have in this unit, we have a qualitative and quantitative descriptions. You guys hopefully know those words by now. In a lab setting, we need to have the right tools in order to accomplish different goals. For example, if I want to weigh something, more or less the only thing that I can weigh something on is a scale. Like, that's pretty straightforward. If I want to measure a volume of something, though, we have a lot of different options. You could measure the volume of something in a beaker. That being said, you probably never would, because beakers are not very precise measuring tools. Like, the lines on the side of a beaker are very far apart. So chances are, if you want to measure something, you want to use a graduated cylinder, a volumetric flask, a pipette, or probably the best instrument we have for measuring a volume is the one we started using in our labs recently, which is the burette. You guys know what I'm talking about, the burette, that long, thin tube, has all those little markings. A burette is a wonderful measuring tool because it is not only accurate if you use it properly, but it's very precise. It's precise to the nearest tenth of a milliliter. Now, a milliliter is very small on its own, but like you should be able to record a value of like 7.1 milliliters. Very, very precise. Does that make sense? Yesterday that I introduced kind of our last topic, and I want to continue that today. The other thing that we might do in a Stoic equation is we might need to know a moles per liter. Like a typical Stoic line of work would be something like this, perhaps. Grams multiplied by moles per gram multiplied by a ratio times by a grams per mole. Where are these grams per mole numbers going to come from? Which is off your periodic table. Where is this grams number going to come from? You'd have to weigh it on a scale. Does that make sense? What if I gave you liters times by moles per liter? See how that kind of accomplishes the same sort of task? Well, where do I get a liters number from? I just use a measuring tool, right? We have so many different things that can measure volume. But fundamentally, there is a huge problem in chemistry if I ask you to calculate a moles per liter number. I said this a lot yesterday, and I will over the next year and half of your chemistry labs. If I give you a solution that says it is 1 mole per liter, can you use that solution? No. I mean, okay, if I give it to you, well, you should hopefully trust me. But like as a scientist, you shouldn't, right? Unless you make it yourself, you really have no way of knowing the authenticity of that value. Does that make sense? And so we need to find a way for you to confirm a moles per liter value so that you know for sure that number is accurate. And that method is called the titration method. That's what I tried to show you yesterday. Ultimately, in a titration, here are the steps. First, you need like a small beaker, and you have to put some solid crystals inside. Do you guys remember what we call those solid crystals? A special name for them. Nope.
Primary standard?
Well done. Yeah, primary standard. In terms of, I think, why we use those words, primary meaning like this is the initial source. We're using something that we are finding ourselves. Like this is step one, not secondary. And standard means some things that are standardized, we should be able to accurately know their concentrations. Can we accurately know the concentration of a liquid? It's hard to. Because what do liquids do? Evaporate. And that causes a huge problem. Is it easy to consistently know the volume and concentration of gas? If you have a seal-proof container, like no leaks, sure. But like, chances are you're going to lose a little bit over time due to some, does that make sense? But if it's a solid, which we can measure on a scale in grams, that is an excellent starting point. So we take a mass, we then divide by a molar mass, and we then do, say, like moles. No, that's not right. We do 1 divided by liters. And basically this solid right here, we add it to water. Then we pour that into a volumetric flask. We fill it up with, usually the volumetric flask is 100 milliliters because that's the size of the flasks that I have. I have a few 250s. But, this will help you then find a concentration. Well, you have now made a solution. We can then use that solution to find a concentration of a different solution. So it's actually a lot of work because this is only step 1. Step 2 then basically says you then need to take the tall burette. You need to put that solution inside the burette and measure how far it requires before it changes color. In the bottom, you need to have a beaker of some type. And you also have to put a known volume in the bottom. Usually, you're using the pipette. That's the world's worst pipette, but hopefully you get the idea. Does that make sense? And usually you have a line of work that looks like this then. There's a liters times by a moles per liter times by a ratio times by 1 over liters. And this will actually find you the concentration of an unknown solution. This liters right here should be coming from the measurement on your burette itself. Sorry, I'm kind of everywhere here. This moles per liter is what you just calculated above. And this liters right here is the size of your pipette. Long story short, grams, easy to measure. Volume, easy to measure. Concentration is a pain in the ass. It's doable, but like it's challenging. Does that make sense? So that's my last topic, talking about how you calculate a moles per liter. Today I want to focus a little bit more on one more thing to do with it. I want to talk about something called an acid-base curve. This kind of goes back to our first unit on solutions. All solutions should either fall into the category of acidic, basic, or neutral. Does that make sense? And this is actually how we're able to know when to stop doing our titration. If you guys recall the one lab we did, the first lab where you guys were like dripping stuff with the little burette, it was supposed to turn white. How did you know when to stop? Visually, you were hoping to see that like no more white solid was being formed, no more white precipitate, but that was really tricky to tell. Does that make sense? So yesterday in the lab, one more thing that I didn't draw in this little drawing, as you're adding, where is it here? As you're adding the titrant to your sample, one more thing you need to do, you need to also put in an indicator. Do you guys remember what indicator we use? Good, phenolphthalein. Do you know why we use that one? There's actually 2 main reasons why. One of them is due to the color change. It's very distinctive. Phenolphthalein goes from clear to pink. Does that make sense? And so it's very easy to tell when it changes color. If we use other indicators that go from, like, say, red to blue, is not as distinctive sometimes because in between red and blue, there's like a purple color. And how will you know when to stop? Like when does it become red? And when does it start becoming like reddish maroon? And when does it start becoming purple? And when does it become blue? Like there's too much of a range. Phenolphthalein is excellent because really there's only two colors. There's clear and then there's pink. There's not like clear and then there's in between. Does that make sense? There's another reason why. It has to do with acids and bases. This is kind of where I was leading to and got distracted a bit. Acids and bases, we've already talked about these. All solutions are either acid, base, or neutral, meaning they have a pH. Does that make sense? What's the pH of an acid typically? Roughly from 1 to 7, give or take. I mean, it can go lower than 1, like you said, negatives. I think you said negatives. Right. What's the pH of something neutral? Yeah, basically 7. Yeah. And what's the pH of something acidic? Sorry, basic. Basic would be like 8 to 14 or so. Does that make sense? Well, this is the second reason why we use phenolphthalein. Can you guys find your data sheets? Like the formula booklet, like the, you know what I'm talking about, this thing. Can you guys find the indicator table? We haven't used this in a long time, but it's on like the second last page. When you add an acid to a base, what's supposed to happen? You're supposed to neutralize each other. Okay. When we are done, completed a titration, I had a phrase for that. We call it the end point. You remember me telling you that word? The end point of a titration is when you're supposed to stop. Okay. And visually, we can tell the end point of a titration because our indicator has changed color. Okay. What should the pH of an endpoint probably be if you're adding acids to bases? 7, yeah. Right? If you add an acid to a base, ideally what's happening is at the point where you change color, the acid and the base are exactly neutralized. And so really the pH should be just slightly above 7 because all of the acid is finally run out. It means that we need an indicator that changes color roughly around the 7 range. So if you guys have your sheets in front of you, indicators that would be useful to use would be probably chlorophenol red would be tolerable because it changes from 5.2 to 6.8. Bromothymol blue is even better because it changes color right around the 7 mark. Same thing with phenol red. Those ones are probably better indicators to use based on their pHs because of the fact that they change color right around the 7 mark. Does that make sense? The problem is we don't use those ones because it's hard to tell when is it yellow and when is it blue because you're going to get like a murky green in between. Does that make sense? So even though phenolphthalein is the next one on the list from 8.2 to 10, even though it's kind of slightly after the 7 mark, and 7 would be ideal, we use it because of the fact that it's better for the color change being visible. Does that make sense? So I think this is a question in one of your upcoming labs. Why do we use phenolphthalein then? 2 reasons. 1, its pH change is relatively close to 7. I know it's not exactly at 7, but if acids and bases neutralize each other at 7, then that makes sense, hopefully. But more importantly, it's color change. It doesn't have a range. It goes clear to pink, not clear to yellow to pink. It's that middle stage that kind of makes it trickier. I have done labs before. I remember I did one in university. I had to use bromothymol blue, and it was really challenging because I had to use my interpretation and figure out when was it yellow, and when did yellow start turning into green, and when did green start turning into blue. Like, it was a lot trickier. Okay. Along with titrations then, if I'm talking about pHs, we've used pH meters before, right? Have you guys do a lab with those? Okay. A pH meter then in theory should be a device that measures the pH of a solution as you do a titration. What we could do actually is make a graph. Okay. Imagine that for a titration, imagine that what you had set up here was something like this. You had an acid. No, let's change that actually. You had just deleted all of it. You had a base as your sample, and you had an acid as your titrate. But let's say that you put a pH meter in the sample. What would the pH be before you even start? Well, bases usually have high pHs, right? So I'd imagine that the pH when you start would be something high, like say 12 or 13, because really what you have when you start in the bottom here is just purely base. Now what happens is you add drop by drop. Remember how like when I added drop by drop it turned pink, but then the pink disappeared? Why did the pink disappear? It was becoming neutralized. And what was happening is there was a whole bunch of particles down in the bottom here, and as you added a particle drop by drop, some of the particles were neutralizing. Essentially, this was your excess, and this was your limiting. And slowly but surely, as you added your excess, the limiting was neutralizing, and slowly but surely, it was all disappearing. Does that make sense? I shouldn't say disappearing, but like neutralizing. Does that make sense? Well, that's kind of what's happening right here in this graph. Is as you add, say, an acid from above, what ends up happening is you still have a base, but you have slightly less base, and so the pH would drop ever so slightly until you reach a certain point. And at that point, all of a sudden, literally all of the like limiting reactant is gone. And then if you add one more drop, it changes color. And that's kind of what happened right here is the graph just all of a sudden tanks. And now if you add any more acid, so if you like keep adding more and more drops, now you have lots of acid down in the bottom of the container. And what's happened is the pH has gone from very high to very low. And somewhere in here, this is where you need to then stop. And again, we had a name for that. Do you remember that name? I said it earlier today. When do you stop? What do we call that? Yeah, this is the endpoint. The endpoint would be defined as this right here, right in the middle of a graph, where all of a sudden the acid and base have exactly neutralized each other, and the endpoint should have a pH of 7. Does that make sense? Because acid and base are completely neutral. If you add even one more drop, it should change the pH drastically. If you add too much, by the way, that's actually when the solution becomes very pink. Remember how I kind of showed you a couple of pictures there where like you want just the faintest of faint pinks? Because if you add too much, then you've overshot your reaction. That's kind of what's happening if you keep adding too much volume, is eventually it just becomes too much over here. In terms of definitions then, I actually like to refer to 7 as the endpoint. And I like to actually use a second word, and you might see this in different literature other places, but I like to call the volume that you use, I call it the equivalence point. They both refer to the same thing. They both refer to the time where you're supposed to stop. Okay? The endpoint refers to the pH when you're supposed to stop. When acid and base have neutralized each other, the endpoint would be 7 because it's neutral. The equivalence point would be how much volume have you used. So you guys remember how a burette is like a 2 measurement instrument where you have to measure the start and finish values? Well, I think in the lab I did yesterday, I used about 4 milliliters. That means that 4 milliliters is my equivalence point. It's the volume required to make acid and base equal. Does that make sense? Long story short, we can graph then what this would look like. This would be the graph of starting with a base and titrating with an acid. Here's some definitions that I just talked about there. There's the endpoint and the equivalent point. Honestly, they refer to the exact same thing. This point right here, right in the middle of that graph, is where the volume should be such that the acid and base are neutral. I feel like I've said the same thing about 5 times, so I'm going to move on. Here's a term I haven't used yet. It's called the buffering area. Have you guys ever heard the word buffer before in different places? Where have you used the word buffer before? You guys haven't done bio yet, have you? Okay, social studies? You guys talk about buffer states in social? Oh, where have you guys heard the word buffer before then? What was that? Okay, that is completely different, so I can't use that as an example. But that, you're not wrong. You had an idea.
Like just the in between.
Okay, that works better for chemistry. Have you guys ever heard of buffer being used as a word to describe like in between two things? Like two people who are fighting, you have to put a buffer in between them, like separate them. Ever heard that phrasing before? Okay. That's maybe a little bit closer to our concept here. It's maybe still not perfect. A buffering area in chemistry refers to an area of very little change. So this is probably just a brand new definition of the word buffer. I guess it has like multiple different meanings. A buffer in chemistry is something that does not change very much. Where on this graph do you have areas that do not change? Right here. That's known as a buffering region. The reason why is the pH, when you start your titration, does not really change all that much. The pH is very constant. What you have is a base. Now, the amount of base you have isn't getting neutralized, but you still have a base. And this area over here would also be known as a buffer. Because once you've neutralized all of your base and all you're doing is you're adding more and more acid, at a certain point, it's acid. Adding more of it doesn't actually change much. It's still acid. Really, this graph right here consists of two buffering regions and then a very narrow region right in the middle, where this region in the middle right here is where drastic change happens. This is the point where your acid and your base have neutralized each other, and all it takes is one drop to violently spike or tank the pH values. So let me just show you some more pictures then. Most of what I need you guys to be able to do is just interpret a graph. So what's happening in this graph here? Well, you're doing some sort of titration. What would the titrant be? The titrant would be the acid, yeah. The sample would be the base. So if you had to draw a bit of a picture here, the titrant would be your HCl. And in the bottom of your flask here, the sample would be NaOH. So what's happening is, if you were to measure the sample's concentration, it's starting off very basic. As you add some acid, does the pH drop? Yeah, a little bit, but not all that much, because ultimately, as you add acid to base, the acid will neutralize a little bit of the base, but there's still base left. Does that make sense? And because there's base left, the pH stays very high. Up until about this point right here. At that point right there, pretty much your last drop of base has finally been neutralized. And if you add one more drop of acid, all of a sudden the pH should just drop. And somewhere in the middle here is a point where it would have been neutral. We're hoping to find that point, because that's known as the end point, or even equivalence point. Does that make sense? How much volume of acid was added then, according to this graph? How much? This is the point we care about right here. I'd say roughly about 24 milliliters. So if you imagine you have your burette, the start and finish values in the burette, you'd use about 24 milliliters. Now, if you kept adding more after the 24 milliliters part, that's not a problem. It just means that your color changes, like you're well past that color change point. Remember, you're looking for like literally the drop that changes color. So if you were to add, like, say 30 milliliters, you're well past that point. Does that make sense? Because we're looking for the point where it's actually right at 7. So what this graph can tell you then is, in the top of your flask, you had HCl. In the bottom, you had hydrochloric. Oh, did I do that wrong? In the top, you had HCl. In the bottom, you have NaOH. You're adding it drop by drop. And the point at which you should have stopped was, give or take, 24 milliliters. What indicator would be a good indicator to use? Well, truth be told, the best indicator based on its pH range is bromothymol blue. Because hopefully you can visually see, bromothymol blue right here changes right around the 7 mark. But again, I said this earlier today, why don't we use bromothymol blue? It's harder to interpret, right? Because you're looking for the place where it was blue and then changes yellow, or yellow to blue. And what if you get like a murky in-between kind of greenish color? It's harder to tell. So even though phenolphthalein technically changes color between about 8 to 10, hopefully you agree that this number right here, if I drop that straight down, is more or less vertically in the same location as where the bromothymol blue one is. Like, it's more or less in the same spot. Now, I wouldn't use alizarin yellow because alizarin yellow would indicate a color change right about here, and that would be way too early. Or if I used orange 4, orange 4's color change is way too late. And so if I used its volume, I'd need about 28 milliliters. And that wouldn't be the equivalence point, right? Because we're looking for the equivalence point where acid and base are the same as each other. Here's just a picture of all the different indicators you could use Basically, so long as the indicator changes color in roughly this sort of spectrum, it's useful. So hence, that's why, again, phenolphthalein, that's why we use it. It is actually possible to have two endpoints. This kind of goes back to something we talked about in our first unit. Do you guys remember the term polyprotic? It's been a while. Do you want to give me an example of a polyprotic acid? So we have multiple reactions. That'll work. Anybody give me an example of a polyprotic acid? Okay, let me write you some acids. HCl, HBr, HNO3, and H2SO4. Which one's polyprotic? H2SO4. Why? The two hydrogens is what makes it polyprotic. Okay. Here's another polyprotic one, H3PO4, because it has three hydrogens. One of the things we talked about a while back, I know it's been, I don't know, a couple months now almost, but these guys right here, they can actually have multiple reactions. Let me write out the reaction for H2SO4. H2SO4 is an ionic, no, it's a covalent compound. And I know that because all of these things are nonmetals. By virtue of being a covalent compound, I need to try to ionize it by adding it to water. If I add it to water, I'm able to make H3O plus and HSO4 minus. Is HSO4 minus a thing? And the answer was yes, it's one of the polyatomics on your table. So therefore, this is an acid. But what we were able to do after that is take HSO4 minus and add it to water. And that would give us H3O plus a second time, and it would give you SO4 2 minus. Is SO4 2 minus a thing? Yeah, it's one of the polyatomics on your table. Why am I done at this point? Why can't I just keep adding it to water? Maybe the best answer is you're out of hydrogens. Does that make sense? Like you had two hydrogens, you ripped one off. You had one hydrogen, you ripped one off. Well, now you have no hydrogens, so now we're kind of done. Does that make sense? Based on this, polyprotic acids and bases have two equations that can occur. Well, if there's two equations that can occur, you can sometimes have a graph that looks like this, where you have two endpoints. Here is the first endpoint, where it's say, let's see, if you're adding an acid, that would be where let's see, if you add an acid, you're going to lose one of your hydrogens. And then here would be the point where you say lose your second hydrogen. Does that make sense? Like you have two reactions occurring. So polyprotics actually can have some weird different graphs. Here's the change though. Where is normally the endpoint pH for acids and bases? Normally you'd say, well, when acid and base they neutralize each other, the endpoint should be at 7. Does that make sense?
Yep.
Where is the endpoint for this titration? Not at 7. Where is the other endpoint for the second half of the titration? Also, not at 7. Does that make sense? That's kind of a weird kind of concept that the acid and base hasn't fully neutralized because there's still more hydrogens left. If you have H2SO4, first you have to neutralize the first hydrogen, then you have to neutralize the second hydrogen. So it is possible to do titrations with literally any indicator. Because if I want to do a titration for this guy right here, I need an indicator that actually takes place about 10 to 12. Or I might need an indicator that takes place from, say, 3 to 5. So normally as I look at my table, methyl orange changes from 3 to 4.4. Normally methyl orange is useless, except if using something polyprotic. In this case, methyl orange might actually be the preferred one. Does that make sense? Because the color changes in the right range.
So would you have to do 2 tests with the 2 different...
What you might need to do then is you might need to use, say, methyl orange, and that would find you this one right here, and you'd have to do, like, say, one set of tests for that. Then you'd have to do a brand new set of titrations, but you'd have to use an indicator up here, like, say, I don't know, alizarin yellow R. Right? And you'd have to do the same work, you have to do it twice, and it would one would find you a volume of, say, like 10 milliliters, and the other one would require a volume of 30 milliliters. And each one you'd have to do independently in order to make this sort of graph. Does that make sense? That was a good question. Here's just kind of some of the equations behind what's happening here. Let's say we have H3PO4. How many reactions can H3PO4 really have? 3, right? Because it's H3PO4. So you could have H3PO4 turn into H2PO4. You could have H2PO4 turn into H1PO4. I didn't even write the one after that, but H1PO4 could turn into H0PO4 by itself, right? Okay, one more thought here. I don't have a slide of this right here, so I think I should put one on there. You see how this graph right here goes downhill? That's not what we did in our graph the other day, though. Like when I did my lab the other day, the demo for you guys, the way my demo worked is in terms of the setup, I actually put the NaOH in the burette as the titrant, and I had put the HCl in the bottom as the sample. How would that change the graph if the HCl was the sample? Good, yeah, it would go up. I think I get what you're trying to do here with your hand. Like it would start low and then whoosh, up high. Sound effects time again, I guess. Does that make sense? So this would be where you start with an acid as your sample and titrate with a base. It actually doesn't matter which one you do. You could either start with acid, end with base, start with base, end with acid. The only issue is based on your color change. It either means you go from red to yellow or from yellow to red. Okay. Most indicators that's not relevant for, but phenolphthalein we almost always have a preference. I would much rather try to figure out when phenolphthalein goes from clear to pink rather than from pink to clear. Does that make sense? Like I think it's way more distinguishable to have no color and then be looking for the first traces of color. So with phenolphthalein, from a practical point of view, we almost always, I cannot think of an exception to be honest, we almost always add the base to the acid. You don't have to, but that's pretty typical. Does that last thought make sense? Yeah. That's it. That's actually all I've got for the unit. So I'd say probably you can break the unit up into 3 main sections. The first section is probably the most of what you're doing. You have to be able to do math calculations. If you can't do stoichiometry calculations at this point, that's like, I don't know, 4/5 of what we do. The second section I need you guys to know about would be like all of the different separation techniques and the qualitative measures. So things like how to use the flame test table, how to use the color table, knowing what a titration and distillation are. And then this is going to be the third thing. If we do a titration, again, the purpose of a titration is to find a concentration. If we wanted to plot a graph, I need you guys to be able to interpret a graph. Okay. I'm not sure whether I'll actually ask you to make a graph. Sometimes I put that on the lab. I don't know whether I've got that on the lab this time around or not. But at the very least, you need to be able to interpret a graph, though, and know what it means. That's our unit. Questions, comments, concerns, conundrums, queries, complaints, criticisms? I'm out of words. You guys are good?
Yeah.
Okay. Take the rest of the day. Try to finish off that assignment and print off those labs. Tomorrow we're going to do 2 labs. Well, tomorrow, Thursday, and Friday we're doing 2 labs. So, cool. We're done.